So without wasting any time, let us get started with the solutions of the problem or the solutions of the questions of data communication network subject of the practice set. So the first question is explain simplex, half duplex and full duplex communication with the help of diagram. So the direction of data flow between two devices is known as the transmission mode. There are three modes: simplex, half duplex, and full duplex. Simplex. Simplex, as the term indicates, communication is unidirectional, that is only one way. That is like a one-way street. Only one of two devices on a link can transmit, the other can only receive. Example of simplex communication is television broadcasting. The broadcast station sends a signal, viewers, TVs receive it, but TVs cannot send a signal back. So there is only a one-way communication called simplex communication. Second is half duplex. Each station can both transmit and receive, but not at the same time. So when one device is sending, the other can only receive and vice versa. The entire capacity of the channel is used for one direction at a time. Examples of half duplex communication are walkie-talkies. So one person presses a button to talk, that is transmitting information, and the other listens, that is only receives. They cannot both talk at the same time. So this is the half duplex communication. Then comes the full duplex communication. Both stations can transmit and receive simultaneously. So the signals traveling in opposite directions share the capacity of the link, either by using two physically separate paths or by dividing the channel's bandwidth. Example of full duplex communication is a telephone conversation. Both people on both sides can talk and listen at the same time. The second question is provide provide a comprehensive explanation of different layers of OSI model, that is Open System Interconnection Reference Framework or Open System Interconnection Model. So the Open System Interconnection, abbreviated as OSI model, is a conceptual framework that standardizes the functions of a telecommunication or computing system into seven abstract layers. The layer number seven is known as application layer. The topmost layer, which interacts directly with the user's software application, is known as the application layer. It provides services for email, file transfer, and other network software services. The functions of application layer are resource sharing, remote file access, virtual terminals, and the protocols supported are HTTP, Hypertext Transfer Protocol, FTP, File Transfer Protocol, SMTP, Simple Mail Transfer Protocol, and DNS domain name system. Layer number six is known as the presentation layer. This layer is responsible for translation, encryption, and compression of data. It ensures that data from application layer of one system is readable by the application layer of another system. The functions of presentation layer are data formatting, that is ASCII to EBCD DIC code, that is American Standard Information Code interchange to EBCD DIC code, data compression, data encryption, or decryption. Formats supported are JPEG, that is Joint Photographic Expert Group, MPEG, Moving Picture Expert Group, GIF. Layer number five is known as the session layer. Session layer manages and synchronizes conversations, that is sessions between two different applications. It establishes, maintains, and terminates connections. The functions of session layer are session establishment, maintenance, and termination. Dialog control, that is half duplex or full duplex, synchronization using checkpoints. API supported for session layer are NetBIOS and sockets. Layer number four is known as transport layer. Transport layer provides reliable end-to-end message delivery and error recovery. It segments data from the session layer into smaller units called segments and reassembles them at the destination. The functions of transport layer are end-to-end flow control, error control using checksum, segmentation and reassembly, connection control. Protocol supported are TCP, that is Transmission Control Protocol, UDP, User Datagram Protocol. Layer number three is known as the network layer. Network layer is responsible for the logical addressing, that is for IP addresses and routing of the packet from source host to destination host across one or more networks. The functions of network layer are logical addressing, routing, packet forwarding. The protocols or devices supported are IP, that is Internet Protocol, ICMP, Internet Control Message Protocol, and routers. Layer number two is known as data link layer. Data link layer moves data across a physical link. It organizes bits from the physical layer into frames and handles physical addressing, that is MAC addresses, error detection, and flow control on the link. The functions of the data link layer are Framing, physical addressing, MAC address, flow control, error control that is cyclic redundancy check, abbreviated as CRC, checksum, access control. Protocols or devices supported are Ethernet, point-to-point protocol, PPPP, switches, bridges. Layer number one is known as physical layer. Physical layer defines the physical characteristics of the network, such as the type of cable, connectors, and signaling method. It transmits raw bits over a communication channel. The functions of physical layer are bit representation, that is encoding, data rate, synchronization of bits, physical topology, transmission mode. The components of the physical layer are cables, for example, twisted pair cable, fiber optic cables, hubs, and repeaters. Next question number three is what are the various popular forms of information? Also explain about five components of data communication. So the popular forms of information are information today comes in different forms, including first type of information is text, that is unformatted or formatted character sequences. Again, ASCII or Unicode. ASCII stands for American Standard Code for Information Interchange. Second type of information can be numbers, that is numerical data represented by bits. Third is images. Images are composed of pixels represented as a matrix of bits, or it forms a bitmap, or by geometric primitives, that is by vector. Fourth type of information can be audio. The representation of audio is a representation of sound, typically as continuous, that is analog form, or digitized, that is digital form signal. Fifth type of information is video. That is the represent video is the representation of the moving pictures, which is a sequence of images or frames displayed at a certain rate. The five components of data communication are a data communication system is made up of five fundamental components. First is message. The message is the information or data to be communicated. It can be of the forms listed above. Second component is the sender. Sender is the device that sends the data message. It can be computer, workstation, telephone handset, video camera, etc. Third is receiver. The receiver is the device that receives the message. It can be computer, workstation, telephone handset, television, etc. Fourth type of component is the transmission medium. Transmission medium is the physical path by which a message travels from sender to receiver. Examples include twisted pair wire, coaxial cable, fiber optic cable, and radio waves or wireless cables. Fifth type of component is the protocol. Protocol is a set of rules that governs data communication. It represents an agreement between the communicating devices. Without a protocol, two devices may be connected but not communicating. Let us come to question number four. Discuss about point-to-point connection and multi-point connection. So point-to-point connection provides a dedicated direct link between exactly two devices. The entire capacity of the link is reserved for transmission between those devices. Characteristics are secure, it is secure and private. Point-to-point connection is having high bandwidth, provides high bandwidth availability. Point-to-point connection is simple to establish. Examples of point-to-point connection are computer connected directly to a printer is an example of point-to-point connection. A remote control and a television, and lease lines connecting two corporate offices are also few of the examples of point-to-point connection. Next comes the multi-point connection. Next is the multi-point connection or multi-drop. A multi-point connection is one in which more than two specific devices share a link. The capacity of the channel is shared either spatially or temporally. Characteristics of multi-point connection are multi-point connection is cost effective as it requires less cabling. Multi-point connection requires a mechanism to manage access to the shared medium to avoid collision or contention. For example, polling or token passing system. Multi-point connection can be less secure as data is sent on a shared line. Examples of multi-point connection are an old-style bus network where multiple computers are connected to a single coaxial cable. Another example of multi-point connection is Wi-Fi network where multiple devices connect to a single access point. Question number 5 is what are the various criteria which a network must be able to meet? So for a network to be considered effective and efficient, it must meet several key criteria. First criteria is the performance. Performance is measured in several ways, including throughput. Throughput is the actual rate at which the data is transferred. It is often less than the advertised bandwidth. Second, performance metric is the delay or latency. Delay or latency is the time it takes for a message to travel from source to destination. It includes propagation time, transmission time, queuing time, and processing delay. Higher throughput and lower delay indicate better performance. Second is the reliability. This criteria is measured by frequency of failure, how often the network fails or experiences errors. Next is recovery time, how quickly the network can recover from a failure, also known as fault tolerance. A reliable network is one that is consistently available and functions correctly. Third is security. Network security involves protecting data from unauthorized access, damage, and modification. Key aspects of security include confidentiality. Confidentiality means protecting data from unauthorized access. Integrity means ensuring the data has not been altered or corrupted during transmission. Availability means ensuring that the authorized users have access to the information and network resources. So this is achieved through mechanisms like encryption, firewalls, and access control policy. Next question is question number 6, that is elaborate extensively on the functions and responsibilities of every layer in TCP/IP, that is transmission control protocol, internet protocol architecture. The TCP/IP protocol suite is the standard model for the internet. It is typically described as a 4 or 5 layer model. The 5 layer model provides a better comparison to the OSI model. First layer is the physical layer. Physical layer in the TCP/IP model corresponds to the OSI layer 1. Responsibilities of the physical layer are to govern the transmission of a raw bit stream over a physical medium. The functions of physical layer are to define the physical characteristics of the medium and the interface, that is the cable type or voltage levels. Physical layer represents bits as electrical or optical signals. Physical layer manages the data rate, that is bit in the form of bits per second. Physical layer handles synchronization of bits. Second layer in TCP/IP model is known as the data link layer. It corresponds to OSI layer number 2. Responsibilities of data link layer is to manage the reliable transfer of data across a single physical network link. The functions of data link layer are first function provided by data link layer is framing, that is dividing the bit stream from the physical layer into manageable data units called frames. Second function performed by data link layer is the physical addressing, that is adding a header containing the physical MAC address of the source and the destination. Third function of data link layer is flow control, that is preventing a fast sender from overwhelming a sole receiver on the same link. It means that sender should not send the data to the receiver at a very fast speed so that the receiver is not able to receive. So this is known as flow control. The third function provided by the data link layer is the error control, meaning detecting and sometimes correcting errors that occur in the physical layer using techniques like cyclic redundancy check, abbreviated as CRC. Fourth function performed by data link layer is the access control, that is determining which device has control over the link at any given time. That is, for example, CSMA CD, carrier sense multiple access, collision detection in Ethernet. Third layer, protocols supported in for data link layer are Ethernet, Wi-Fi. Wi-Fi is nothing but 802.11 standard, PPP, point-to-point protocol. Third layer in TCP/IP model is known as the network layer or the internet layer. It corresponds to OSI layer number 3. Responsibilities of network layer are network layer is responsible for moving packets from source host to destination host, which may be in different networks. The functions of network layer are, first function is logical addressing. Network layer provides a global unique address for each host on the network, for example, an IP address. Network layer also provides routing as one of the functions, that is determining the best path for a packet to travel from source to destination across multiple networks. That is also known as internetworking. Routers operate at this layer. The third function performed by network layer is the packetizing, that is encapsulating transport layer segment into packets or datagrams by adding a header with source and destination IP addresses. That is, header contains source and destination IP addresses. Protocols supported with network layer are IP, that is Internet Protocol version 4 or version 6. ICMP, that is Internet Control Message Protocol. IGMP means Internet Group Management Protocol. The fourth layer in TCP/IP model is known as the transport layer. It corresponds to OSI layer number 4. Responsibilities of transport layer are to provide the logical communication between processes running on different hosts. The functions of the transport layer are as follows. First function is process to process delivery. The transport layer uses port numbers to deliver data to the correct application process on the host. Second function performed by the transport layer is segmentation and reassembly. That is, transport layer split the application layer messages into smaller segments and reassembles them at the destination. The third function performed by the transport layer is connection control. That is, it can be connection oriented or connectionless. Example of connection oriented is TCP, that is transmission control protocol. Example of connectionless protocol is the UDP, that is user datagram protocol. The next function performed by the transport layer is the flow control. That is, transport layer provides end-to-end flow control to avoid overwhelming the destination host. It means that source host should not send the packets or data data at a very fast rate so that the receiver is unable or the destination is unable to handle. Next function performed by the transport layer is the error control. So the error control means that transport layer provides end-to-end error checking and recovery. Transmission control protocol uses checksums, acknowledgements, and retransmissions for the purpose of error control, for ensuring the error control. Protocol supported are transmission control protocol TCP. It is a reliable protocol, also connection oriented, whereas user datagram protocol UDP is a unreliable or connectionless protocol. Fifth layer in TCP/IP model is known as the application layer. It corresponds to OSI layer number 5, 6, and 7. Responsibilities are: application layer enables user applications to access network services. The TCP/IP model combines the functions of OSI session layer, presentation layer, and application layers into this single layer called application layer. Functions of the application layer are as follows. Application layer provides standard interfaces for applications like web browsing, email, and file transfer. Application layer handles data representation, encoding, and dialog control. Protocols supported with the application layer are Hypertext Transfer Protocol, File Transfer Protocol (FTP), and SMTP, Simple Mail Transfer Protocol, DNS Domain Name System, and Telnet. Next question is question number 7, that is using diagram describe about mesh topology, star topology, bus topology, and ring topology in detail. So first of all, I'll be telling you mesh topology. In mesh topology, every device has a dedicated point-to-point link to every other device. A fully connected mesh network has n into n-1 divided by 2 physical links for n devices. As you can see here in the diagram, this is the mesh topology. You can see here this is the mesh topology, right? And the advantages of mesh topology are: mesh topology is reliable and robust. That is, failure of one link does not affect the rest of the network. Mesh topology is also secure. Data travels on a dedicated link, providing security. Mesh topology also provides easy fault identification. It is easy to isolate the link that has failed. The demerits or cons or disadvantages of mesh topology are: mesh topology is very expensive because it requires a large amount of cabling and input-output ports. Mesh topology requires complex installation. It is very difficult to install and reconfigure the mesh topology. So these are the diagrams of each of the topologies. Star topology, as you can see, in the form of a star. Ring topology in the form of a ring. This is the mesh topology. Bus topology means in the form of the bus. As you can see here, this is the bus to which 4 devices are connected. Okay, so this is the diagram for all the topologies. Now we are discussing the advantages and disadvantages of next topology called star topology. In the star topology, all devices are connected to a central controller known as hub or switch. Devices do not have direct links to each other. Advantages of star topology are: star topology is easy to install and reconfigure. That is, we can add or remove devices in a simple manner. Star topology is also robust. That is, failure of one link only affects one device. Also, star topology provides easy fault isolation. The disadvantages of star topology are: single point of failure. If the central hub or the switch fails, the entire star topology or the network goes down. Cost. Star topology also requires more cabling than a bus topology. The next topology is the bus topology. Bus topology is a multi-point topology where all the devices are connected to a single shared cable called the backbone or the bus. Terminators are used at both ends of the bus to absorb the signal and prevent reflection. Advantages of the bus topology are: bus topology is inexpensive. That is, bus topology uses less cable than other topologies. Bus topology is also easy to install. Demerits are: bus topology is difficult to reconfigure and it is also difficult to isolate the faults in bus topology. Single point of failure: a break in the main cable can disable the entire bus or the entire network. Signal degradation: performance degrades as more devices are added into the bus topology. Next is the ring topology. In ring topology, each device has a dedicated point-to-point connection with only the two devices on either side of it. A signal is passed along the ring in one direction from device to device until it reaches its destination. Advantages of ring topology are: ring topology is easy to install. Ring topology provides orderly access, that is, each device gets a turn to transmit through the token passing mechanism, preventing the contention or collisions. Demerits of ring topology are: ring topology, traffic is unidirectional. So a break in the ring can disable the entire network. This can be reduced with dual rings, mitigated or reduced with dual rings. Also, ring topology is difficult to reconfigure. That is, adding or removing a device disrupts the whole network. Next question is question number 8, that is, explain about performance, reliability, and security in detail. Performance, reliability, and security are the three fundamental criteria for evaluating a network's effectiveness. First is performance. Performance refers to the speed and efficiency of data transmission. It is measured by several key metrics. Performance is measured by bandwidth. Bandwidth is the theoretical maximum capacity of a link measured in bits per second or BPS. It is the width of the pipe. Next performance metric is known as the throughput. Throughput is the actual measured rate of successful data transfer, which is often lower than the bandwidth due to overhead, traffic, and errors. Third performance metric is known as latency or delay. Latency or delay is the total time it takes for a bit of data to travel from source to destination. Latency or delay is the sum of all these, that is, sum of propagation delays, transmission delay, and queuing delay, and processing delay. Propagation delay is the time for a bit to travel the length of the medium. Transmission delay is the time to push all of a packet's bits onto the link. Queuing delay is the time a packet spends waiting in queues in routers. Processing delay is the time for routers to process the packet header. Also, latency delay consists of another part that is known as jitter. Jitter is the variation in latency of packets. High jitter is problematic for real-time applications like video conferencing and online gaming. Next metric is known as the reliability. Reliability indicates the dependability and availability of the network. It is crucial for mission-critical applications. Availability is usually expressed as a percentage of uptime, that is 99.99% 5 nines availability. It is the probability that the network is functioning correctly at any given time. Fault tolerance. Reliability can also be measured through fault tolerance. The ability of fault tolerance is the ability of the network to continue operating, possibly at a reduced level even after the failure of one or more components. This is often achieved through redundancy, having duplicate components, having redundant links, routers, or power supplies. Metrics are mean time between failure, that is MTBF, and MTTR, that is mean time to repair. Mean time between failure is the average time the network operates without a failure, and mean time to repair is the average time it takes to repair a failure and restore the network to full operation. Reliability can be measured by the ratio of MTBF, that is mean time between failure, divided by the sum of both, that is sum of mean time between failure and the mean time to repair. Next is security. Security involves the protecting the network and the data transmitted over it from unauthorized activities. The core principles of network security are often summarized by the CIA triad. Security consists of all these aspects. First aspect is the confidentiality. Confidentiality means ensuring that the data is only accessible to the authorized users. This is primarily achieved through encryption. Security also consists of the aspect integrity. Integrity means ensuring that data is not altered or corrupted during transmission, either accidentally or maliciously. This is verified using mechanisms like checksums and digital signatures. Security can also be determined in terms of availability. Availability is ensuring that the network and its resources are available to authorized users when they need them. Security threats to availability include denial of service attacks. Mechanisms for security are: security is implemented using tools and policies like firewalls, antivirus software, intrusion detection system, that is IDS, access control list, that is ACL, and user authentication. The next question is question number 9. Question number 9 says that identify the key attributes that determine how efficiently a data communication system operates and describes each of these attributes in depth. The efficiency and effectiveness of a data communication system are determined by the Four key attributes. First attribute is the delivery. Delivery means the system must deliver data to the correct destination. Data must be received by the intended device or user and only by that intended device or user. This is ensured by using proper addressing mechanisms like MAC addresses at the data link layer and IP addresses at the network layer. Routers and switches use these addresses to forward data to its correct destination. Second is accuracy. The system must deliver the data accurately without any alteration. Data that has been corrupted during transmission is often unusable. This is achieved through error detection. Techniques like checksum, parity check, and CRC, that is cyclic redundancy check, are used to detect if errors have occurred in the data. Error correction. If an error is detected using any of the above methods, the system should have a mechanism to either correct the error, which is known as forward error correction, or request a retransmission of the corrupted data, as done by the transmission control protocol. Third is the timeliness. The system must deliver data in a timely manner. Data delivered late is useless in many applications. Real-time transmission. In applications like video conferencing, telephony, and online gaming, data must be delivered with minimal and consistent delay. Next is jitter. A key aspect of timeliness is low jitter, which is the variation in packet arrival time. High jitter can disrupt the playback of audio and video streams. Protocols like RTP, that is real-time transport protocol, are used to manage timeliness for such applications. Fourth is the efficiency. The system should deliver data with minimal overhead and minimal resource usage. Throughput is a measure of how many useful bits are transmitted per second. High throughput is always desirable. Protocol overhead. Protocols add headers and tailors to the data, which consume bandwidth. An efficient system minimizes this overhead while still providing necessary services like addressing and error control. Next is resource management. Resource management is the efficient use of network resources like bandwidth and router processing power, which further ensures that network can handle more traffic and users effectively. Now we come to question number 10, that is explain the concepts of analog and digital signals with appropriate illustrations. Compare and contrast their modes of representation by highlighting the fundamental distinctions between them. Analyze the limitations of analog signals, particularly focusing on their susceptibility to degradation during transmission. Furthermore, using suitable diagrams, demonstrate why digital signals exhibit greater resilience to noise compared to analog signals. So, answer is analog and digital signals. An analog signal has infinitely many levels of intensity over a period of time. It is continuous. Analog signal is a continuous signal and can take any value within a range. A sine wave is a perfect example of an analog signal. Analog signal is represented by the continuous waveforms. Examples of analog signal are human voice, music, and video. Next is the digital signal. A digital signal can have only a limited number of defined values. Digital signal is always discrete. Often these values are as simple as ones and zeros, that is representing two levels. A square wave is a common representation of a digital signal. A digital signal is represented by the discrete voltage levels. Examples of digital signal are data stored in the computer's memory. Now we can compare and contrast the analog signals with the digital signals based on their features. First feature is nature. As I have earlier said, analog signal is a continuous signal, whereas digital signal is a discrete signal. An analog signal can carry infinite values in a range, whereas digital signal represents finite discrete values, either 0 or 1. Next feature is representation. Sine waves are a very perfect representation or example of analog signal, whereas square waves is an example of digital signal. Examples of analog signal are human voice, radio waves. Example of digital signals is computer data. Next feature on the basis of which we can compare and contrast the analog signal with the digital signal is the noise effect. Analog signals are highly susceptible to noise, whereas digital signals are more resilient to noise. It means noise can degrade the quality of the analog signal, whereas noise have a little effect on the quality of the digital signal. There are some of the limitations of limitations of analog signals. So the first limitation of analog signal is susceptibility to degradation. Analog signals are highly susceptible to degradation, especially from noise. Noise is any unwanted electrical or electromagnetic energy that corrupts the signal. So now the problem is when noise is added to an analog signal, it is difficult or impossible for the receiver to distinguish the original clean signal from the new corrupted signal. So each time the signal is amplified to a combat attenuation. Attenuation means the weakening of a signal. The noise is also amplified. This leads to a progressive degradation of the signal quality over long distances. So analog signals are susceptible to noise, whereas digital signals are more resilient to noise. So resilience of digital signal to noise means digital signals are much more resilient to noise, meaning a digital signal consists of discrete voltage level, that is plus 5 for a 1 or 0 volt for a 0. When noise is added, the voltage level might fluctuate, but as long as it does not cross the threshold that distinguishes a 1 from 0, the original value can be perfectly recovered. A device called repeater or regenerator can receive a degraded digital signal, determine the intended sequence of zeros and ones, and then regenerate a brand new clean signal for the next leg of the journey. This prevents the accumulation of noise. Clear? So this is the diagrammatic explanation of the analog and digital signal. On the left hand side, you can see on the x-axis we are having time, on y-axis we are having signal. So this is the example of a analog signal. On the right hand side, we can see the digital signal. Now we come to next question, that is question number 11. 11 question number says that explain the concept of a composite signal with a suitable illustration. Consider a signal formed by combining three sinusoidal components with frequencies f2, f5f and amplitudes 10a, 4a, 2a respectively. Depict these individual components in both the time domain and frequency domain. So a composite signal is a signal made up of many simple sine waves with different frequencies or amplitudes and phases. According to Fourier analysis, any periodic composite signal can be decomposed into a series of simple sine waves. So signal components given to us are frequency f, amplitude is 10a, frequency 2f, amplitude is 4a, frequency 5f, amplitude is 2a. Now first representation is the time domain representation. In the time domain, we plot the signal's amplitude against time. Each component is a sine wave. The composite signal is the sum of these three waves at each point in time. Component 1, that is frequency f and amplitude 10a, is sine wave with a long period and high amplitude. Component 2, that is 2 times frequency and 4a amplitude, that is a sine wave that completes 2 cycles in the time. Component 1 completes 1. Its amplitude is 4a. Component 3, that is 5f and 2a, 5f as the frequency and 2a as the amplitude, represents a sine wave that completes 5 cycles in the time. Component 1 completes 1. Its amplitude is 2a. Now, a diagram would show three separate graphs. The first wave is wide and tall. The second is twice as fast and less than half as tall. The third is 5 times as fast and 1/5 as tall. A fourth graph would show their sum, a complex jagged but periodic waveform. Now we are going to discuss frequency domain representation. In the frequency domain, we plot the signal's amplitude or power against frequency. This representation is much simpler for a composite signal. It consists of vertical spikes at the frequencies of its components. A diagram would have frequency on the x-axis and amplitude on the y-axis. There would be a vertical line, that is a spike at frequency f with a height of 10a. There would be another vertical line at 2f frequency with a height of 4a. There would be a third vertical line at frequency 5f with a height of 2a. The space between the spikes would be 0. And this is the diagrammatic representation of all these components. Component 1, that is f10a, component 2, 2f 4a, component 3, that is 5f 2a, and the last, this brown signal represents the composite signal, right? On the x-axis represents time, that is in arbitrary units, and y-axis represents the amplitude, that is a, right? Next question is question number 12. That is, a periodic signal occupies a bandwidth of 30 Hz. So we have been given the bandwidth as 30 Hz and highest frequency component is given as 90 Hz. Determine the corresponding lowest frequency. Also sketch the frequency spectrum, assuming that all frequency components have equal amplitude. So we want to determine the lowest frequency. So the bandwidth of a signal is the difference between its highest and lowest frequency components. So the formula is bandwidth equal to highest frequency minus lowest frequency. Bandwidth is given to us as 30 hertz. Highest frequency has also been given to us as 90 hertz. So we have to calculate this lowest frequency. So apply this formula: bandwidth equal to highest frequency minus lowest frequency. So bandwidth is 30 hertz. 30 hertz equal to highest frequency is 90 hertz minus lowest frequency. So lowest frequency will become 90 minus 30, that is 60 hertz. So this is the first answer to the given problem, right? So the lowest frequency component of the signal is 60 hertz. 60 hertz as we have now computed using the above formula, right? Second solution, we have to sketch the frequency spectrum. The frequency spectrum is a plot of amplitude versus frequency. The problem states that all the frequency components have equal amplitude. The signal exists in the range from 60 Hz to 90 Hz. So the x-axis will represent frequency in Hertz. The y-axis will represent amplitude. Since the signal contains all the frequencies in the range and they have equal amplitude, the spectrum is a horizontal rectangle starting at 60 Hz and ending at 90 Hz. So this is the diagram. As you can see, on the x-axis we are having frequency in Hertz. On the y-axis we are having amplitude. So the amplitudes are equal for minimum and maximum frequency. Bandwidth is given as 30 Hz. Next question is question number 13. That is 13. Question number says that using appropriate diagrams, provide a comprehensive explanation of circuit switching and packet switching techniques, highlighting their operational mechanisms in detail. So first of all, we will be discussing the concept of circuit switching. The concept behind the circuit switching says that circuit switching is a dedicated physical path or circuit that is established between the source and destination before communication begins. This circuit is reserved for the entire duration of the session, whether data is being sent or not. Now, the operational mechanism behind the circuit switching is first of all, the connection. The first step is the connection setup. In connection setup, a dedicated path is established through the network switches from source to destination. Resources like bandwidth or switch capacity are reserved along this path. This causes an initial delay. The second step in circuit switching is the data transfer. That is, the data is transmitted along the dedicated path at a guaranteed constant rate. There is no addressing information on the data itself as the path is fixed. The third step in circuit switching is the connection teardown. When the session is over, the circuit is terminated and the reserved resources are released. So this diagram represents the circuit switching, as I have explained in these three steps. First step is the connection setup. As you can see in the diagram, source initiates the connection, and then particular data is transferred to the destination, and then this phase one. Phase one is the connection setup, where the connection is being established between source and destination. So as you can see, source is initiating the connection, and in between there are two switches being used, switch A and switch B. Those are also known as reserved channels, and destination accept the connection. Second step is the data transfer. So this is the diagram representing the second step. In the second step, as the term itself speaks, data is transferred from source to destination through these two switches. The third step, once the communication is over, the connection is tear down. That is, connection is terminated between source and destination, right? So this is all about the circuit switching, and these are some of the characteristics of the circuit switching. The advantages of circuit switching are it provides guaranteed bandwidth. There is no congestion after connection setup. Delay is also constant, and circuit switching is ideal for real-time voice and video. Demerits or disadvantages of circuit switching are: circuit switching is inefficient for bursty data, that is, resources are wasted during idle periods. There is some delay in connection setup. Examples of circuit switching is traditional public telephone network, that is PSTN, also known as public switch telephone network. So this is all about the circuit switching. Next comes the packet switching. The concept behind the packet switching says that data is broken down into small blocks called packets. Each packet is sent independently through the network. There is no dedicated path. The mechanism for packet switching consists of these steps. First step is the packet creation. The source device breaks the message into packets, adding a header to each packet with source, destination, and sequence information. Second step is the transmission. Packets are sent into the network one by one. At each switch or router, the packet is stored briefly, that is also known as store and forward mechanism. Its destination address is examined and it is forwarded to the next hop on the path toward the destination. The third step is the reassembly. The destination device reassembles the packet in the correct order to recreate the original message. So this is the diagram representing the packet switching. So the first is data fragmentation when the original message is divided into these fragments. Second step is routing with queuing, that is these packets are transmitted from source to destination. Third is packet reassembly, that is all these packets are reassembled at the destination. So this is the diagram, right? Characteristics of packet switching are, first of all, what are the advantages of packet switching? Packet switching provides efficient use of network resources, that is links, because links are shared. Packet switching is also robust because can route around failures. In packet switching, there is no connection setup delay for individual packets. Also, packet switching is ideal for busty data like web browsing and email. Demerits of packet switching are packet switching provides variable delay, that is jitter. There is also a potential for collision or there is also a potential for congestion or network congestion in packet switching. Packet switching also requires complex protocols for reliable delivery. Example of packet switching is the internet. Now we come to question number 14. Question number 14 says, a signal enters a transmission line with an attenuation rate of minus 0.4 decibels per kilometer and an initial power level of 5 milliwatts. Determine the remaining signal power after it has propagated to a distance of 8 kilometers, right? So, first of all, we have to calculate the attenuation. First of all, you should know what is attenuation. Attenuation is the weakening of a signal. When a signal gets weakened, it is known as attenuation. So, or the loss of a signal, you can say. So, attenuation is the total loss in decibels. So, the total loss in decibels is the attenuation rate multiplied by the distance. So, total attenuation formula is rate into distance. So, the rate is given to us as minus 0.4 decibels per kilometer and distance is also given as 8 kilometers. We multiply both these quantities and we get the total attenuation as minus 3.2 decibels, right? Now, we have to use the decibel formula to find the final power. The formula for attenuation in decibel is, this is the formula for attenuation in decibel, that is 10 into log 10 P2 by P1, where P1 is the initial power and P2 is the final or remaining power, right? Now, in this case, we have to determine this final or remaining power, that is quantity P2. All remaining quantities are given to us. For example, total attenuation we have recently find out as minus 3.2. So we substitute here minus 3.2, right? And 10 into log 10 P2 we have to determine, and in the question itself P1 is given as 5 milliwatts. So by substituting all these values, we can determine the value of P2 as 5 into 10 to the power minus 0.32, right? So this is the you can convert this power. This is power in watts. You can convert it into further into milliwatts. So the answer is P2 equal to 2.39 milliwatt as the answer. So we have successfully solved this question, right? Next question is question number 15. Question number 15 says, clearly define attenuation, what is distortion, what is noise in the context of data communication, supported by well-labeled diagram. Explain the underlying reasons for signal weakening in transmission media and describe the method used to quantify this loss. Additionally, explain how attenuation is computed when signal power values at two different points are known. If a signal's power drops to 1/4 of its original value during transmission, calculate the attenuation in decibels. If an amplifier increases the signal power by a factor of 20, determine the corresponding gain in decibels. So, as I have earlier explained to you, attenuation is the weakening of a signal strength. Distortion is the alteration or corruption of its shape or form. Noise is the addition of unwanted signal. So, attenuation is quantified in decibel by comparing signal power at 2 points. In our question, it dropped to one. We have given it dropped to 1/4 of the original power correspond to. So this is the answer. So we will be calculating this answer later on in the solution of this question. And also in the question, we have been given that amplification by factor of 20. And the second answer we have to determine is 13 decibel, which we will now calculating. So see the solution to this problem now. So the first term is attenuation. The definition of attenuation is loss of signal strength. As I have earlier told you, that is the uh, weakening of a signal. So attenuation is nothing but loss of signal strength as it travels through a medium. The cause of attenuation is the resistance of wires, absorption in optical fibers, or spreading in wireless channels. Attenuation can be measured in decibels, comparing input and output power. The formula for attenuation in decibel is 10 into log 10 P power input power divided by output power. Second term we have to determine is the distortion. Distortion is the change in the shape of the signal waveform. The cause of distortion is different frequency component traveling at different speeds, that is dispersion or non-linearities in the medium. The effect of distortion is signal becomes unrecognizable or misinterpreted at the receiver. Third is the noise. Noise is nothing but unwanted signal that interfere with the original transmission. Types of noise are thermal noise, crosstalk is also a type of noise, impulse noise, and intermodulation noise. The fact of the noise is error. It can cause errors in data interpretation. Also, it can reduce clarity. The reasons for signal weakening are electrical resistance in copper cables, absorption and scattering in optical fibers, free space path loss in wireless communication, imperfect connectors and splices causing leakages, causing leakage. Now, the quantifying attenuation means attenuation can be measured in decibel using the logarithmic scale. So, if the signal power at a point A is represented by P1 and at point B is P2, attenuation in decibel is equal to 10 into log 10 P1 by P2. So, in the question, we have to find out the solution to two parts. First part is we have in the question we have been given that signal drops to 1/4 of the original power. That is P out is P in divided by 4. That is signal drops to 1/4 of the original power. That is original power is P in and P out is P in divided by 4. So attenuation will be 10 into log 10. So if we divide P in divided by P in divided by 4, it becomes 4. So the value of attenuation comes out to be 6.02 in decibel. So the answer is 6 decibel attenuation, right? So we have found the answer to first problem, where in the question we have been given signal drops to 1/4 of the original power. So the answer is 6 decibel. Second, we have to determine, it has been given to us that amplifier increases power by a factor of 20. So the output power is equal to 20 into input power, because we have been given in the question amplifier increases the power by a factor of 20. So gain is equal to 10 into log 10 20, and it will come out to be 13.01 decibel. That is answer is rounded about 13 dB, right? And this is the diagram which has been asked in the question. The attenuation, distortion, and noise. All these are the represent the transmission impairment. It means that we do not get the exact signal at the or original signal at the receiver side. Here, this diagram represents the distortion, right? So all these are. So attenuation diagram shows signal weakening across transmission medium. Distortion diagram illustrates waveform shape change. Noise diagram displays unwanted interference. Noise diagram displays unwanted interference added to the signal. So in summary, attenuation, distortion, and noise are the three main impairments in data communication. Attenuation is measured in decibel, and both loss and gain can be calculated using the logarithmic ratios of signal power. In our example, 6 decibel is the attenuation and 13 decibel is the gain we have found. Right? Now we come to next question. That is question number 16. Question number 16 says that using suitable diagrams, provide a detailed explanation of amplitude shift keying, phase shift keying, and frequency shift keying, emphasizing their working principles and characteristics. So, amplitude shift keying abbreviated as ASK, phase shift keying abbreviated as PSK, and frequency shift keying abbreviated as FSK are the three fundamental digital modulation techniques. They differ in how the carrier signal is altered to represent binary data. ASK varies amplitude, whereas PSK varies phase, and FSK varies frequency, as the term indicates. First is amplitude shift keying, or ASK. Working principle behind the amplitude shift keying says that in ASK, the amplitude of the carrier signal changes according to the digital input. Binary 1 represents high amplitude carrier, binary 0 represents low amplitude or no carrier. Characteristics are: amplitude shift keying is simple to implement. Amplitude shift keying is susceptible to noise and interference since the amplitude is easily distorted. Amplitude shift keying is used in optical fiber communication and RFID systems. Second is phase shift keying, or PSK. The working principle behind the phase shift keying says that in PSK, the phase of the carrier signal is shifted to represent binary data. Binary 1 means carrier with phase 0. Binary 0 means carrier with phase 180. That is in binary phase shift keying. Characteristics of phase shift keying are: phase shift keying is more robust against noise compared to amplitude shift keying. Phase shift keying variants include binary phase shift keying, quadrature phase shift keying, and higher order phase shift keying, that is MPSK. Phase shift keying is widely used in Wi-Fi networks, satellite communication, and cellular networks. And the last is frequency shift keying, or FSK. Working principle behind the frequency shift keying says that the frequency of the carrier signal changes according to the digital input. Binary 1 means high frequency carrier, binary 0 represents low frequency carrier. The characteristics of frequency shift keying are: frequency shift keying is more resistant to noise than amplitude shift keying. Frequency shift keying requires larger bandwidth compared to amplitude shift keying and phase shift keying. Frequency shift keying is commonly used in modems, Bluetooth, and radio communication. This is the diagram representation of all these three: ASK, PSK, and FSK. Clear? So you can refer to this diagram to distinguish between ASK, PSK, and FSK. Right? Now we can also draw a table to differentiate it between these three. That is ASK. First, on the basis of the in amplitude shift keying, parameter is amplitude. In PSK, parameter is phase. In frequency shift keying, parameter is frequency. Next is noise resistance. Noise resistance is low in ASK, high in PSK, and moderate in FSK. Bandwidth requirement is low in ASK, moderate in FSK, and high in moderate in PSK and high in FSK. Applications of ASK is used in optical fiber and RFID systems. PSK is used in Wi-Fi, satellite communication, cellular communication. FSK is used in modems, Bluetooth, and radio communication. Right? ASK is the simplest but least robust. PSK offers strong noise immunity and is widely used in modern communication systems. FSK balances simplicity and robustness but requires more bandwidth. Next question is question number 17, which explain the concepts of ideal, that is noise-free channels, and practical, that is noisy channels. Determine the signal to noise ratio, that is SNR. SNR means signal to noise ratio, and its value in decibels for a perfectly noise-free scenario. So first of all, we are going to discuss the ideal channel, that is in that case there is where there is no noise, that is noise-free. In practical, we are never having the ideal channel. Noise is always there. But for explanation, first of all, we would like to define the ideal channel, which is noise-free channel. So this is the theoretical. It is not practical. This is the theoretical communication channel where no noise or any other impairment is introduced to the signal during transmission. The only limitation on the data rate is the channel's bandwidth. The maximum data rate for a noise-free channel is given by the Nyquist bit rate formula. Next is the practical noisy channel. This is a real-world communication channel where signals are always subject to impairments like noise, attenuation, and distortion. The capacity of a noisy channel is limited by both its bandwidth and signal-to-noise ratio. The theoretical maximum data rate is given by the Shannon capacity formula. Now, SNR means signal-to-noise ratio for a perfectly noise-free scenario. In a perfect noise-free scenario, signal to noise ratio is the ratio of the average signal power to the average noise power. Because there is no noise in the noise-free scenario, so noise is zero. So that's why signal to noise ratio is infinity, which is never practical. SNR is infinity. We can also calculate the signal to noise ratio in decibels. For that, we are having a formula, that is signal to noise ratio in decibel is given by this formula 10 into log 10 this signal to noise ratio, right? So this is the formula for signal to noise ratio in decibel, right? So because signal to noise ratio in noise free channel is infinity, we substitute here infinity, and log 10 infinity is infinity. So signal to noise ratio in decibel is equal to infinity decibel in for a perfectly noise free scenario. Next is the for a perfectly so sorry, for a perfectly noise free channel, SNR is infinite and SNR in decibel is also infinite, right? Next is the question number 18. Question number 18 says assume a highly disturbed channel where the SNR approaches zero, that is where the signal to noise ratio is zero. Evaluates its channel capacity. We have to calculate the capacity. So the theoretical maximum capacity of a noisy channel is given by the Shannon-Hartley theorem. Formula is capacity C is given by bandwidth B into log 2 1 plus signal to noise ratio. So C, as I have said, is the channel capacity in bits per second, that is BPS. B is the, as I have said, B is the bandwidth of the channel in hertz, that is Hz. And SNR is the signal to noise ratio. Please remember, this is only signal to noise ratio and not in signal to noise ratio in decibel. Both are different. Signal to noise ratio is different. Signal to noise ratio in decibel is different. So it is only signal to noise ratio and not signal to noise ratio in decibel, right? So we are given that channel is highly disturbed. Channel is highly disturbed. So there is very large quantity of noise in there. So that's why signal to noise will approach zero here. Signal will be zero, noise will be very much, right? So we substitute the value of signal to noise ratio here because signal is zero, noise is very large. So signal to noise ratio will be zero. So 1 plus 0, log 2 1 is 0 and multiplying bandwidth B into 0 will result in 0. So capacity will be 0 bits per second. So conclusion is when the signal to noise ratio approaches 0, meaning that noise power is almost very large or larger than the signal power, that is signal is 0 and noise is very large, channel capacity also becomes 0. This means it is impossible to transmit any information reliably over such a channel. We cannot, it is almost impossible to transmit any information in such a case, right? Now we come to question number 19. Question number 19 says, if a signal has a power of 20 milliwatts and the accompanying noise power is 2 microwatt, compute both signal to noise ratio as well as signal to noise ratio in decibel, right? So first of all, we have to convert both power value to the same unit, that is watt. We have been given first power, signal power is given as 20 milliwatt. So we convert into watt by multiplying it by 10 to the power minus 3. Noise power is given as 2 microwatt. We convert this quantity is also into watt by multiplying by 10 to the power minus 6. Now we can compute both quantities, that is signal to noise ratio as well as signal to noise ratio in decibel. First we calculate signal to noise ratio. So signal to noise ratio is simply the ratio of signal power and noise power. So signal power is given as 20 into 10 to the power minus 3 volts, and noise power we have been given to us as 2 into 10 to the power minus 6 volt, and that's why signal to noise ratio will become 10,000, right? Now we'll be computing signal to noise ratio in decibel. For that we are having a formula, right? Signal to noise ratio in decibel can be computed by using this formula 10 into log 10 signal to noise ratio. So signal to noise ratio we have just computed as 10,000. So we substitute here 10,000, right? We substitute here 10,000 and signal. So this 10,000 may be written as 10 to the power 4, right? So it becomes log 10 10 to the power 4. So it will become log 10 10 to the power 4 will be equal to 4. So 10 into 4 will be equal to 40 decibel. So the signal to noise ratio in decibel comes out to be as 40 decibels as our final answer, right? We now come to question number 20. Question number 20 says, consider a noiseless channel with a bandwidth of 4 kilohertz. Calculate the maximum achievable bit rate when the system uses binary signaling. Binary signaling means 2 levels. Recalculate the bit rate when 8 signal levels are used, each level representing 3 bits, because if there are 8 signal levels, number of required bits is 2 raised to power 3. That is 3 bits are needed, right? Compare the two results and determine the increase in transmission rate, right? So for a noiseless channel where there is no noise, we use the Nyquist bitrate formula. So Nyquist bitrate formula is this formula, that is capacity C equal to 2 into bandwidth into log 2 L. L is the number of levels, right? So C is the maximum bitrate, that is in bits per second, BPS. B represents here the bandwidth in hertz, and L is the number of signal levels. So here we have been given bandwidth is given to us as 4 kilohertz, right? Has been given to us as 4 kilohertz. So 4 kilohertz means 4 kilohertz into 1000, 4 into 1000, 4000 hertz, right? And we have binary signaling, that is number of levels are 2. So L is equal to 2, right? L is equal to 2. So we have to calculate the maximum bit rate. So C1 will be equal to, what is the formula? Formula states that C equal to 2 into bandwidth. So 2 into bandwidth. Bandwidth is 4000 hertz into log 2 L. L is the number of levels. How many levels are there? 2. So substitute number of level as 2. So log 2 is 1. 2 into 4000 is 8000. So 8000 into 1 is 8000 bits per second, right? Or we can also call it as 8 kbps or 8 kilobits per second, right? So the first answer is 8 kilobits per second, right? Second, this is the answer to the first problem asked in our question, that is maximum bit rate is 8 kbps. Second, in the second part, number of signal levels are 8. So the value of L is 8. So remaining things are same. Only the value of L is 8. So again substituting all these values. So log 2 8 means log 2 8 can be written as 2 raised to power 3. So log 2 raised to power 3 will be equal to 3. So 2 into 4000, 8000, 8000 into 3 is 24,000 bits per second, or you can also say as 24 kilobits per second. So this is the answer to the second problem, right? Now further, what has been asked? It has been asked to compare the two results and determine the increase in the transmission rate. So you can easily see in the first, transmission rate is 8 kilobits per second. In the second, transmission rate is 24 kilobits per second. So the transmission rate is tripled. In the first case, transmission rate is 8 kbps. In the second case, transmission rate is 24 kbps. So the transmission rate is tripled, right? You can also determine the difference of these two. 24 minus 8 is 16,000 bits per second, or you can also say transmission rate is tripled. So we have completely now solved this problem, right? Now, the next problem, that is question number 21. Question number 21 says that suppose a transmission rate of 300 kbps is required over a noiseless channel with a bandwidth of 25 kilohertz. Compute the minimum number of signal levels needed, right? So we use the Nyquist bitrate formula and show the number of levels. In this question, number of signal levels we have to compute. That is value of L we need to compute, right? So formula again remains the same. C is equal to bit rate equal to 2 into bandwidth B into log 2 L, where L is the number of level. We have to calculate the value of L. So transmission rate in the question is 300 kbps, or you can say 300 into 1000, that is 300,000 bits per second. So the value of C is 300,000 bits per second. Bandwidth is given in the question as 25 kilohertz. So value of B bandwidth is 25 kilohertz. That is 25 into 1000, 25,000 hertz, right? So we substitute the value. C is 300,000 bits per second equal to 2 into bandwidth. Bandwidth is 25,000 hertz into log 2L. We have to calculate the value of L. Simply solve this equation. We divide 300,000 by 50,000. It becomes 6. So value of L will be 3. Log 2L is 6. So value of L will be 2 raised to power 6. If we solve this, logarithmic equation, that is log 2L equal to 6. In that case, the value of L will come out as 2 raised to power 6. That is 2 raised to power 6 is nothing but 64. So the minimum number of signal levels needed is needed are 64 is the answer, is the final answer, right? So we have successfully found a solution to this problem. Now the next problem is question number 22. Question number 22 says that calculate the theoretical highest bit rate of a regular telephone line. A telephone line normally has a bandwidth of 300 hertz. That is, minimum is 300, maximum 3300 hertz. So obviously, highest we subtract lower from higher. So 3300 minus 300 is 300 hertz, right? Assigned for data communication. Signal to noise ratio is also given to us as 3162. We have to calculate the theoretical highest bit rate of this telephone line, right? So since this is a noisy channel, because telephone line is a noisy channel, we use the Shannon capacity formula to find the theoretical highest bit rate. Formula is C. So C is the highest bit rate with that we need to determine. Formula is bandwidth B into log 2 1 plus signal to noise ratio. Bandwidth is given to us as 300 hertz. So the value of B is 300 hertz. That is nothing but 3300 minus 300. That is 3000. It is given to us. Signal to noise ratio SNR is also given to us as 3162, right? So it is also now we substitute. We have simply have to substitute the values. Bandwidth is 300 hertz. We substitute value of B as 3000. Log 2L 1 plus signal to noise ratio is 3162. So 1 plus 3162 will become 3163. So we now to calculate this logarithmic value log 2 3163. What we will do? We will be using another formula. There is a formula called log 2x equal to log to the power log to the base 10x divided by log to the base 10 2. So in that case, the value of x is what? Value of x is 3163, right? So we have to determine log 2 3163. This we need to determine, na? So value of x is 3163, right? So we can log 10. Sorry. Okay. So we have to determine log 2 3163. So the value of x is 3163. Formula says log 2x is given by log 10x divided by log 10 2. So we substitute the value of x here 3163. So log to the base 10 3163 is, you can calculate, use the calculator, value will be come out to be 3.50, and log to the base 10 2 is, again you can use the calculator, value will come out to be 0.301. So we divide 3.50 by 0.301. We will get the value of this quantity, that is come out to be 11.62, right? So now we simply multiply 3000 by 11.62. We will get the required answer. So required answer is 34,860 bits per second. So this is the highest bit rate. So the theoretical highest bit rate of the telephone line is approximately 34,860 bits per second, or you can also say as 34.86 kilobits per second, right? So we have successfully found out the solution to this problem, right? Next question is question number 23. So the question number 23 says that assume that 6 communication channels, we are having number of communication channels are 6, right? Each occupying a bandwidth of 150 kilohertz. They need to be combined into a single transmission link. If a guard band of 15 kilohertz is required between adjacent channels to avoid the interference, determine the minimum total bandwidth necessary for the composite signal. So number of things we have been given to us. Guard band of 15 kilohertz is given to us. Bandwidth of 150 kilohertz is given to us, right? So scenario describes the frequency division multiplexing or FDM. So first of all, we have to calculate the total bandwidth for the channels. The number of channels are 6. It has been given in the question. The number of communication channels are 6. So number of channels are 6. Bandwidth per channel is 150 kilohertz, right? So total channel bandwidth will be, because there are 6 number of channels, total channel bandwidth will be number of channel, that is 6 into bandwidth per channel, that is 150 kilohertz. So the total channel bandwidth will be 900 kilohertz, right? Now we have to calculate the total bandwidth for guard band. Total channel bandwidth is 900, and see, guard bands are usually placed between the channels. So because there are number of channels are 6, obviously the number of guard bands will be 6 minus 1 5. So n minus 1 number of guard bands will be n minus 1. If there are n channels, the number of guard bands will be n minus 1. So number of channels are 6, number of guard bands will be 6 minus 1, 5. So bandwidth per guard band is given to us in the question as 15 kilohertz. So we are having 5 guard bands. So total guard band bandwidth will be 5 into 15, that is 75 kilohertz. So the total bandwidth will be 900 plus 75. So the total bandwidth will be 900 plus 75, that is 975 kilohertz. So we have now successfully calculated the total bandwidth. So the minimum total bandwidth necessary is 975 kilohertz. So I think this is the final answer, right? So this is the final answer. The total bandwidth is necessary required is 975 kilohertz, right? Now the next question, that is question number 24. Question number 24 says that a bit sequence 111000011 is obtained at the receiver. Apply the CRC, that is cyclic redundancy check technique, with a generator 1001 to verify the correctness of the received sequence, right? Now, to verify the correctness of a received sequence using CRC, that is cyclic redundancy check, the receiver divides the entire received sequence, that is data plus CRC, by the same generator polynomial. Generator polynomial is also known as the divisor. If the remainder is 0, the sequence is considered correct. So the received sequence is given to us as 111. It has been given in the question. 111000011. This is the received sequence, right? And the generator divisor is also given to us as 1001. So simply we will divide this quantity by this quantity, right? We will divide received sequence by a divisor, right? If the remainder is 0, the sequence is considered correct. So when we divide this quantity by this quantity, we have to perform the binary division. Always remember, binary division means using XOR for subtraction. Usually when you perform the division operation and when you put some quotient, then you do the subtraction operation now. But in this case, in place of subtraction operation, we have to perform the XOR operation. XOR means 0 0 will result in 0, 0 1 will result in 1, 1 0 will result in 1, 1 1 will result in 0. XOR operation you know now. So simply we divide, this is the quotient. When we will dividing this quantity by this quantity, this quotient will come. Clear? And when we, these 4 bits, when we are subtracting these 4 bits, when we are subtracting these 4 bits from these 4 bits, we have to take the XOR operation, right? This is the XOR operation result, right? So whenever you are doing this subtraction, this is we have to do the XOR. In place of subtraction, we have to do the XOR operation. Again, so binary division, you know, when you divide this quantity by this quantity, quotient will come out to be this. Quotient will be this, right? Quotient will be this, and remainder will eventually come out to be 0. Because remainder is coming out to be 0, since the remainder of the division is 0, the cyclic redundancy check passes. This indicates that the received sequence is correct and no errors were detected. To check the correctness of the received bit sequence using CRC with, let us go step by step. So these are the detailing step of division. You can do yourself, right? Answer will remain same. Final remainder we will getting 0. When we perform the binary division operation and we replace subtraction by XOR, finally we are getting the remainder. These are the detailed steps of division operation, right? Nothing more. So the remainder is 0, received sequence is correct. When the remainder is 0, it means the received sequence is correct. There is no error has been detected now, right? So this is the solution to this problem. Now the next question is question number 25. Describe the procedure used to compute a checksum in data communication systems using the binary sequence. This is the binary sequence, right? Now you have to calculate the corresponding checksum. First of all, we have to tell the procedure. How can we calculate the checksum? Then we have to solve a numerical problem for this binary sequence. For this binary sequence, we have to calculate the checksum, right? So first of all, I am going to tell you the procedure. Using that procedure, you can find out the solution to this numerical problem, right? So the checksum procedure is how to calculate this checksum. First step in calculating the checksum is to divide the data. This is the data given to us. This is the data. Number of bits are given. This is the given data. We have to divide this data into two parts. So data to be sent is divided into two equal size segments, in two equal parts, typically of 16 bits, right? Then we have to sum those two segments. That is, after dividing, we have to take the sum of those two segments, right? So all the segments are added, and you have to perform the addition of both of them using the one complement arithmetic. Remember that whenever you are adding these two segments after division, after dividing these many bits into two equal parts, two equal parts will be added to each other using one's complement arithmetic. That is what is the one's complement arithmetic? That is, in one's complement arithmetic, if there is a carry out from the, we have to do the simply the binary addition. But one's complement arithmetic says that addition says that if there is a carry from the most significant bit, then you have to add that carry into the least significant bit. That is known as the one's complement arithmetic addition, right? After calculating the sum, you have to simply take the complement of that sum. Complement of that sum means you have to convert 0 into 1, 1 into 0. That is the complement, right? After that, we have to do the verification. At the receiver, all the received segments plus the received checksum are added together. So this complemented value is the checksum, right? What we have to do, all the received segments plus the received checksum are added together, right? If the result is a sequence of all ones, that is accepted, right? So now I am going to solve this problem. This is given to us. This binary sequence is given to us. Divide this into two parts. I think it will be 00 4 times 1 0 triple 1 0. So we have to divide this into two parts, right? First part is this highlighted part, and second part is this. No. Just a minute. 110. Okay. Uh-huh. So first part is I think this highlighted part, and second segment is this unhighlighted part. So segment 1 is highlighted, segment 2 is this unhighlighted part, as you can see. So the first step is divide the data into two segments. Okay, first step is over. What does the second step say? We have to add both of these segments, segment 1 and 2. How we have to add these two segments? By taking the ones complement arithmetic addition. So we can take the binary addition. You know what is binary addition. So there will be a carry. So carry will be added. Carry of this one will be the carry. This will be added into this result. Whatsoever is the result of the addition, will be adding that one into the least significant bit. Right. Now, after this is the next step, that is adding the carry. After adding the carry, we have to take the complement. So after this is the result. Now we have taken the complement of this sum. So the complement is the required checksum. So this is the first answer. This is the checksum. So corresponding checksum is this, right? So by following these steps, we can calculate the checksum, right? So we have successfully solved this problem also. Now we come to problem number 26. Problem number 26 says that for the polynomial expression given by x raised to power 8 plus x raised to power 4 plus x raised to power 3 plus x plus 1, derive its equivalent binary divisor using the generator polynomial given by, compute the cyclic redundancy check for the polynomial x raised to power 4 plus x raised to power 3 plus 1 data sequence this. So there is some typographical error in this question. I'll be telling you in the solution to this question. So see my answer. Question number 26. See the answer to question number 26. So see. So as I said, this question appears to have a typographical error. This question combines two separate problems. I will be solving two parts as intended. Part 1, we have to solve two problems. Part 1 problem is we have to derive the binary divisor from the polynomial. This polynomial is given to us, right? So how to calculate the divisor? To convert this to a binary divisor, we write a 1 for each power of x present. So those powers of x which are present, we have to multiply, we have to write 1 for them, and those powers of x which are not present, we have to write 0, right? For example, x raised to power 8 is present, so we will be writing multiplying 1 by x raised to power 8. But power 7 is not present, so we will be writing 0 into x raised to power 7. I hope you understand. X raised to power 6 is also not there, so we write 0 into x raised to power 6. X raised to power 5 is also not there, so we write 0 into x raised to power 5, right? But x raised to power 4 is present here, so we write 1 into x raised to power 4 and not 0 into x raised to power 4, right? So we now note these 1 and 0. 1, 0, 0, 0, 1, 1, 0, 1, 1. So this is the solution to first problem, that is we have successfully found out the divisor, right? So in this manner we can calculate the binary divisor from this polynomial itself. I hope you have understood the answer to this problem. In the second part, we have to compute the cyclic redundancy check code, CRC code. So the question means to say, this is the polynomial x raised to power 4 plus x raised to power 3 plus 1, right? Compute the CRC for the data sequence. This original sequence is given to us. We name this sequence as M. This is the original M sequence. Original sequence is represented by M, right? Original sequence is given to us. Now, first step is to determine the generator and parameter, which we have earlier done. So for those power of x which are present here, we write 1 here. For example, x raised to power 4 power is present, so 1 into x raised to power 4. X raised to power 3 is also present, so 1 into x raised to power 3. But x raised to power 2 is not present, so we write plus 0 into x raised to power 2. X raised to power 1 power is also not present, so plus 0 into x raised to power 1. Plus 1 can also be written as x raised to power 0, so it is present, so 1 into x raised to power 0, right? So generator G will be this 1, 1, 0, 0, 1, 1, 1, 0, 0, 1, right? In this manner. Now the degree of the polynomial is 4. How we can determine degree? Because highest power is x raised to power 4. So the degree of this polynomial is 4. So R is 4. So we need to append 4 zeros to the data. What is the data? Original data. This is the original data. We append 4 zeros at the end of this. We append 4 zeros at the end of this original data given to us, right? And then we perform this division. That is, now we divide this whole quantity. We divide this highlighted whole quantity by this generator 11001, right? And if the remainder is, again we have to, whenever you are doing this subtraction, this is the quotient, this is the divisor, this is the dividend. Whenever you are doing this subtraction operation, we have to take the again XOR, right? As I have earlier told you. And remainder is 1001. So what we have to calculate? We have to calculate the part 2. In the part 2, we have to calculate the CRC, cyclic redundancy check code. So the original data was this M, and remainder we have to append at the end of this. That will be the answer to the problem, that is CRC check code, that is cyclic redundancy check code. So this is the original data M, and we append the remainder at the end of this. Sorry. So this was the original code. CRC bit is the remainder. CRC bits are the remainder of the division is 1001. So this is the CRC bits. Sorry, this is the CRC bits, and the frame to be CRC will be 1001. CRC bits will be remainder, that is 1001. This is the remainder, and the frame to be transmitted would be the original data. Original data was represented by M, which was also given to us. This was the original data M, and now we append CRC, 4 CRC bits at the end of this. That is the remainder. That will be this remainder will be appending to the end of the original data, that is M, which is also given to us in the problem. So this will be the whole quantity will be the, what will be it? It will be the frame to be transmitted. it will be the frame to be transmitted. As it has also been written, that is the original data followed by the this 4-bit CRC code, right? So we have successfully solved this problem. However, there was a typographical error in this problem, right? Now we jump to question number 27. Question number 27. Explain the step-by-step process involved in generating a cyclic redundancy check code. Determine the CRC bits for the data sequence this using the divisor. This we have already solved. So this type of problem just we recently solved. Nonetheless, for the sake of completeness, let us solve this problem as well. That is 27. So this is the step-by-step CRC generation process. First of all, agree on a generator. Both sender and receiver agree on a generator polynomial, which is the binary number of r plus 1 bits. That is the degree of polynomial is r, right? Append zeros. The sender appends r0 bits to the end of original data message m, created an augmented message m dash. Divide. The sender performs binary division of the augmented message m dash by the generator g. Division is done using modulo 2 arithmetic, that is subtraction means XOR. Find the remainder. The remainder of the division will be r bit long, that is called as CRC. Then we create the frame. Sender replaces the r appended zeros in the augmented message with the r bit CRC remainder. This new data plus CRC is then transmitted to the receiver. So now solve this. However, we have just solved this type of problem, right? So what we have been given, data sequence has been given to us as this. This is the data sequence, right? This is the data sequence, and divisor is 1001, right? Divisor is 1001. What will we be doing? First of all, this is the original data. This is the original. How many bits are there? 6 bits. So the value of k is 6 bits, right? This is the original data m. This is the original data m. Number of bits in this original data are 6 bits. That is value of k is 6 bits. Divisor is 1001. How many bits are there? 4 bits. 4-bit means the value of r plus 1 is 4. Remember, students often commit mistakes here. They take value of r as 4, but here the value of r plus 1 is 4. So the value of r will become 3. 4 minus 1 will become 3. Now, we will be appending how many number of zeros to the end of this original message? 3 zeros, because value of r is 3. So we will be appending 3 zeros. We will be appending 3 zeros at the end of this original message m, original data m, right? And then we divide this whole quantity by this divisor. And then what will be the remainder? This remainder will represent CRC, that is cyclic redundancy check code. And we will be appending this remainder to the end of the original message m. What is the original message m? This is the original message m. 00. So at the end of this original message m, we will be appending the remainder. That will be the frame transmitted. So the transmitted frame is, this was the original message highlighted. As you can see, highlighted is the original message, and what so is the remainder, that is also CRC. We append the CRC to the original message m. That will be the whole will be the transmitted frame, right? We have just solved this in problem number 26, right? So we have successfully solved the problem number 27 also. Now we jump to problem number 28. 28 problem says that explain the working principles of frequency division multiplexing, that is FDM, time division multiplexing TDM, and wavelength division multiplexing WDM using appropriate diagrams highlighting their operational differences, right? So what is multiplexing? Multiplexing is a technique to combine multiple signals into one signal over a shared medium. First is FDM, frequency division multiplexing. Principle behind FDM is an analog technique that divides the bandwidth of a single physical medium into several smaller non-overlapping frequency bands. Each band is a separate channel and is assigned to a different user or signal. To prevent interference, the channels are separated by thin, unused strips of bandwidth called guard bands. Working of the FDM. At the sending end, a multiplexer modulates each signal onto a different carrier frequency. These modulated signals are then combined into a single composite signal. At the receiving end, a demultiplexer uses filters to separate the composite signal back into its original component signals. So this is the example of FDM is AM, FM radio broadcasting and analog cable TV. So this is the diagram comparing FDM with TDM and WDM, right? You can draw this diagram if the question appears in your exam, right? Now we explain TDM, that is time division multiplexing. Principle behind TDM is a digital process that allows several users to share the same transmission medium by allocating a different time slot to each user. Each user gets to use the full bandwidth of the channel, but only for a short period of time. The time slots are grouped into frames, and each frame contains one or more slots dedicated to each user. Working of the TDM. The multiplexer takes a chunk of data from each input line in turn, combines them into a single frame. The frames are then transmitted over the high-speed link. The demultiplexer at the receiving end separates the data based on the timing and directs it to the appropriate output line. The diagram I already drawn. Example of TDM is digital telephone systems, that is T1 even lines or ISDN, integrated switch whatsoever it is. This is an example. Next is wavelength division multiplexing, WDM. Principle behind WDM is an analog multiplexing technique conceptually similar to FDM but designed for use with fiber optic cables. It combines multiple data streams by transmitting them simultaneously on different wavelengths, that is colors of light. Each wavelength acts as a separate channel. Working of WDM, that is working of wavelength division multiplexing. At the sending end, a multiplexer often using a prism or diffraction grating combines multiple light sources of different wavelengths into a single beam that is transmitted over one fiber. At the receiving end, a demultiplexer splits the light beam back into its component wavelengths and directs them to their respective receivers. Example of WDM is backbone of the modern internet is an example of WDM. Long haul communication links is also an example of WDM. Now we jump to question number 29, which says that sketch digital waveforms representing signals with 2 levels and 8 levels. If a signal employs 16 distinct levels, determine how many bits are encoded per symbol. So, digital waveform sketches 2-level signal, that is a binary. The waveform alternates between two discrete voltage levels, that is 0 volt and 5 volt. This is essentially a digital signal with logic 0 and 1. 8-level signal, the waveform can take 8 distinct amplitude levels. Each symbol represents one of these 8 possible values. So the waveform looks like a staircase with 8 possible heights. Imagine the 2-level waveform as a square wave flipping between 2 heights, while the 8-level waveform has multiple possible step heights instead of just 2. Now we have to calculate the bits encoded per symbol. The number of bits per symbol is determined by this formula, that is bits per symbol equal to log 2 number of levels. For 16 levels, we will substitute value 16 here, log 2 16, so 4 bits are encoded per symbol. So the 4 bits are encoded per symbol. This is the solution to our problem, right? So in summary, 2-level waveform represents a binary square wave, that is 0 and 1. 8-level waveform is a staircase like signal with 8 possible amplitudes. 16-level signal will require 4 bits per symbol. So this is the diagram illustrating 2-level signal and 8-level signal. On the x-axis we are having time, right? So these two diagrams representing 2-level signals and 8-level signals. So the image now shows both 2-level and 8-level digital waveform side by side. The 2-level signal is a square wave flipping between logic 0 and 1. You can see this flipping between 0 and 1. This is 0, then 1, 0, 1, 0, 1, 0, 1. It is square wave. 2-level signal is a square wave, whereas 8-level signal has multiple discrete steps. You can see here multiple steps, showing how symbols can occupy any of 8 distinct amplitudes, right? So as we worked out earlier, if a signal uses 16 distinct levels, how many bits per symbol required are? We have just calculated. 4 bits are encoded per symbol for 16 levels. For 16 distinct levels. Finally, we jump to last question, that is question number 30. Question number 30 says, discuss how bandwidth and SNR influence the achievable data transmission rate. Further describe the methods used to compute channel capacity for both ideal and noisy communication channels. So, influence of bandwidth and signal to noise ratio. Bandwidth is represented by B. Bandwidth is the range of frequencies a channel can pass. It is directly proportional to the achievable data rate. A wider bandwidth is like a wider pipe. It can carry more data per unit of time. Doubling the bandwidth roughly doubles the maximum possible data rate, all else being equal. Signal to noise ratio is abbreviated as SNR. Signal to noise ratio, that is SNR, measures the strength of the signal relative to the background noise. A higher SNR means the signal is clearer and easier to distinguish from noise. This allows for more distinct signal levels L to be used reliably. Since each level can represent multiple bits, that is log to L, a higher SNR allows for a higher data rate. The relationship is logarithmic, so doubling the SNR does not double the capacity, but it does increase it. In summary, both a wider bandwidth and a higher SNR are desirable for achieving a higher data transmission rate. What are the methods to compute channel capacity? We have already solved several numerical problems pertaining to that. So when we are having noise-free channel, that is ideal, which is never practically possible. But for that, method is to use the Nyquist bitrate formula given by C equal to 2 into B, where B is the bandwidth, log 2 L. L is the number of levels. So this formula gives the theoretical maximum bitrate, never the practical. Gives the theoretical maximum bitrate for a channel with bandwidth B using L discrete signal levels, assuming there is no noise. It shows that for a given bandwidth, the data rate can be increased by increasing the number of signal levels. However, in the real world, the number of levels is limited by noise. Then comes the noisy channel. In noisy channel, the method is to use the Shannon-Hartley theorem, that is the Shannon capacity. Formula is C equal to bandwidth B into log 2 1 plus signal to noise ratio, that is SNR. So this formula gives the not the theoretical. This formula gives the practical maximum bit rate, that is the capacity C. It is wrongly written here. It is the practical maximum bit rate. For a noisy channel with bandwidth B and signal to noise ratio SNR, this is an absolute upper limit for reliable communication, regardless of how many signal levels or what kind of modulation is used. It tells us the ultimate potential of the channel. To approach this capacity, in practice, one needs very sophisticated error correction codes. With that being said, we have successfully solved all the questions or problems, numerical problem, theoretical questions provided in the practice set. And best of luck for your midterm examination of data communication and networking. Thanks to all.